Hi, class. So this is the lecture for chapter 13.2, and it's going to cover equilibrium constants. You probably should have read that section of the chapter first before you watch the video. I think it'll make more sense to you. Let's see, what else? There's two worksheets we're going to do in this chapter, so you should probably print those out so you can work on them at the end. When we finish the lecture, that's worksheet 10 and worksheet 11. And to be prepared to do those worksheets, you probably want to have a pencil, paper, scratch paper, a notepad while you watch the lecture to take down notes, jot down things that I say are particularly important, and a calculator. So I think that's about it. So let's get started. I'm looking down at my notes here once in a while. So I'm going to screen share and we'll start the PowerPoint. As usual, I'll go through the PowerPoint and then we'll do the worksheet. The PowerPoint is a little bit long this time. That's why I split this lecture on 13.1 and 13.2 into two parts. So I'm going to share my screen, but before I do that, I'll stop the video. And here we go. So let's start with chapter 13.2 on equilibrium. So there are a lot of things in this subchapter 13.2 in chemical equilibrium. Some of the learning objectives. So I've split them into 5 main topics. Learn what the equilibrium constant is, and that's there are actually a couple ways, not a couple ways you can write it, but several names for this expression that we're going to write for the equilibrium constant. Learn how it is determined, how it changes with conditions or summing, and summing chemical equations like in Hess's law. So if we have equilibrium expressions for 2 or more reactions, then we add them together or subtract them. What do we do with the equilibrium constant? And then learn how it is applied to non-equilibrium conditions and learn how it is used in gaseous equilibria. So let's get started. Remember, an equilibrium equation is written something like this. I think there's no significance to the large B, that's a typo. And I don't know what that C is doing down there, but we'll go ahead. So this is the equation, a generic equilibrium equation. A plus B goes to C plus D with the corresponding coefficients in lowercase letters. And you can write, there's a mass action expression that you can write. It's called the mass action expression. We're going to call it the reaction quotient, which is a quantity that describes the status of a reversible chemical reaction in terms of the molar concentrations of the reactants and products. So that's key, the molar concentration. So that's how we're going to express the amounts of the reactants and the products. So the way this reaction quotient is written, like I said, sometimes called a mass action expression, is like this. It's simply the products, the concentration of the products multiplied together. So it's the concentration of C times the concentration of D raised to the power of the coefficient in the balanced equation. So let me repeat that again, in the balanced equation. So when you're given a problem, you have to make sure the equation is balanced because those coefficients go into these mass action or this reaction quotient expression. So it's concentration of C raised to the power of a C, the concentration of D raised to the power of D, divided by the concentration of the reactants raised to the power of the coefficient. And in this case, is A to the A and B to the B. So that's called our reaction quotient. I've given it a lowercase c to indicate concentration, because sometimes these mass action expressions of the reaction quotients, the third thing we're going to call it is the equilibrium constant, is expressed in different concentration values. So in this case, we're going to call it Q sub C for concentration. So I've written down here what we need to be able to write this. It's an equilibrium reaction and a balanced equation. So being able to write this is a key skill. And this is the first thing we're going to do on our worksheets, is to write these expressions for different reactions. So when a reaction quotient, a reaction quotient when the system is at equilibrium is called the equilibrium constant. So when we talked about what equilibrium means before, it's when the concentrations of the reactants and the products don't change. So when those concentrations are constant, when we're at that steady state, then the reaction quotient becomes an equilibrium constant. Other than that, it's not an equilibrium constant. So this reaction quotient, let me repeat that, this reaction quotient is only called an equilibrium constant when the system is at equilibrium. Any other time, it's a reaction quotient. So Q equals C is identical. So QC is identical to KC at equilibrium. So what does that mean? That means the equilibrium constant, the Kc, has the same form as the Qc. So we can write our Kc then, an equilibrium constant, as C to the C, D to the D, A to the A, B to the, divided by A to the A, and B to the B, which is simply the product of the products. Product means multiplied, the concentrations multiply together, over the product of the reactants raised to the powers determined from their reaction coefficients in the balanced equation. So you can see the form is the same. They're easy to write. So that's what the equilibrium constant would look like. Now, the reaction quotient is not a constant. Okay, the reaction quotient can be any value. So any reaction where you know the concentration of the reactants and the products, you can plug them into this expression. And if it's not at equilibrium, it's called the quotient, the reaction quotient. We're going to look more at that, how the reaction quotient and the equilibrium constant compare and what that means for the reaction. When the system is at equilibrium, then that's called the equilibrium constant. So the equilibrium constant is always the same. The concentrations don't have to be the same, but the product concentrations multiplied together divided by the reactant concentrations multiplied together are always the same. Always have the same value. So I have an example of that. The only thing that changes the value of the equilibrium constant is temperature. So the equilibrium constants are always stated at a specific temperature. And room temperature, 25 degrees C, is a very common temperature to state the value of the equilibrium constant. There's no way to predict what the equilibrium constant is going to be. That's determined experimentally. So writing these equilibrium constant expressions is important, but it's just like writing the reaction quotient expression. So let me just say one more thing about this. The equilibrium constant is constant at a specific temperature, but it changes with temperature. So that's important to know that it's going to change at a different temperature. Later on, we're going to talk about the equilibrium constant for water. And that is stated at 20 degrees, I think, C, or 25 degrees C is what we usually use it at. But that equilibrium constant changes. It's not, if we're talking about boiling water, it's the equilibrium constant is different because that's at 100 degrees C. So write an equilibrium expression for the following reaction. So first of all, I have it in red there, it must be balanced. So what does that look like? So we're going to write the the products concentration in molarity. So this is in molarity raised to the power. So CO2, molarity of CO2 squared divided by the reactant concentrations to the power of the coefficient times each other. So we have CO, carbon monoxide, squared times the concentration of oxygen. So these are, that should be a subscript, K subscript C. Well, maybe not necessarily. Later on, we're going to find out, since this is a gaseous reaction of just gaseous reactants and products, that we can express this equilibrium constant in terms of pressure. So that would be a K sub P. We'll see that in a later slide. So that's how you write it. So something about equilibrium constant. Let's think about that. It's the ratio of the products over the reactants. So if the equilibrium constant is about 1, it means the concentration, that value, the reactants over the products, means those are both about the same. That means it's a moderate reaction. It doesn't really favor reactants or products. So equilibria can either favor the products or the reactants. In chapter 13.1, we were looking at the equilibria between N2O4 and NO2. And in that case, there was always more N2O4. So that equilibrium favored N2O4, which was a reactant. So if the equilibrium constant is very large, that means we have mostly products. That makes sense, right? It means the product, the value of the product is greater. The amount of product is greater than the amount of reactant. We have product over reactant. So a large Kc means there's more product. If there's a small Kc, it means it's mostly reactant. It means that little reaction takes place. And this is the case for weak acids. So a large Kc is what happens with strong acids. It means there's lots of product. And a small Kc, less than 1, means the acid stays mostly in its acid form. It doesn't ionize to form hydrogen ion in water. So it doesn't, not much reaction takes place. So let's look at manipulating equilibrium constants. So let's see. Given a reaction and its equilibrium constant, we can easily calculate the equilibrium constant for variance of that reaction. Okay, so variance of that reaction would be if we added that reaction to another reaction, or if we change the reaction. Remember, equilibrium reactions go forward and backwards. Well, what if we have an expression for a forward reaction? That means we can write the expression for the reverse reaction, and we know what that value is if we know the value of the equilibrium constant for the forward reaction. So the equilibrium constant reaction in the reverse is the reciprocal. So in this case, we've seen this reaction before, N2O4 to 2NO2. So you write the equilibrium constant expression as NO2 squared divided by N2O4, products over reactants, and that's equal to 0.214. If we reverse it, the reaction, we have 2NO2 in equilibrium with N2O4. The equilibrium constant would be N2O4, which is the product now, over NO2 squared, which is the reactant. That's just the inverse of the former equilibrium constant. So just take the inverse of 0.212 and you get 4.72. Notice this is the equilibrium constant at 100 degrees C. So here's another way we can manipulate the equilibrium constant. Suppose we have 2 N2O4s. We multiply all the coefficients by 2. Well, what does that do to our equilibrium constant, our Kc? Well, if we multiply all the coefficients by 2, we end up with 2 N2O4 in equilibrium with 4 NO2. We write the equilibrium expression for that reaction, that equilibrium reaction is NO2 to the 4th divided by N2O4 to the 2. That is simply the original equilibrium, the one above it, squared, right? If we square that, we're going to get NO2 to the 2. And let me see, sometimes I can annotate this. Let me see if we can annotate it. Oh, there's an annotation thing. So I'm gonna annotate this a little bit. So I'll use this pen. So we're gonna multiply this. We're gonna square it. If we do that, we get this down here. So we would just simply square this, 0.212, and that's what we have here. So if we squared that, I don't know why the answer is here, but you could just square that on your calculator and have the answer. Okay. Go down to the next page. So the equilibrium constant for a net reaction made up of 2 or more steps is a product of equilibrium constants for individual steps. So here we have 2 reactions. We have H2CO3, carbonic acid, and water, produces some hydrogen ion plus bicarbonate ion. This subscript A means that's the equilibrium constant for an acid. That's what that A means. Okay, so the subscripts tell you something about the reaction or something about what's in that equilibrium constant. In this case, we're still doing molar concentrations, moles per liter. So this equilibrium constant for the first reaction is 4.3 times 10 to the minus 7th. If we look at what happens when you form bicarbonate, well, bicarbonate can also be an acid. So you put bicarbonate in water and it can split into an acid, H3O plus, hydronium ion, plus carbonate ion. That has an equilibrium constant of 5.6 times 10 to the minus 11. You can see that's much smaller than the previous one. And both of these, because they're small, means both of these equilibria favor the product side. So overall, if we add these two together, you get H2CO3 plus 2 H2O is in equilibrium with 2 H3O plus 2 hydrogens plus carbonate. So the question would be, how much carbonate is formed? Well, what you would do when you add 2 reactions together to get a third reaction, you would multiply the equilibrium constants together. So K overall was Ka1 times Ka2. And you can prove that if you write the equilibrium constant for this reaction, for the last reaction, you can prove that it's just the first reaction equilibrium expression times the second reaction equilibrium expression. You can derive this. So if you multiply those 2 equilibrium constants together, you get 2.4 times 10 to the minus 18. Well, that's really a small number. So that means hardly any carbonate ion is formed. So you could just very confidently say, I don't know how much is formed, but it's not going to be very much. It's really, really slight. Look at that number, 2.4 times 10 to the minus 18. Extremely small. Okay, next slide. So the other thing we have to consider is heterogeneous equilibria. Heterogeneous means that the solutions that are in equilibria are not gases or in water, AQ, but they're solids or liquids. So remember, we have 4 states we usually talk about for chemicals and in chemical reaction. We have solids, liquids, gases, and aqueous. And we indicate those with the subscripts. Well, the only concentrations that are important in an equilibrium expression are those for aqueous solutions, because they have molar concentrations. We can describe that as moles per liter, or gases, because we describe those concentrations as moles per liter. Solids, the concentration is so huge that it really doesn't change during the reaction, so you don't have to. So solids, and the same for liquids. So solids and liquids are not included in the equilibrium expression. So if you look at the first one, lead, so we have lead chloride, and we've added water to it. So that's what this means. When you add water to it, you get lead ion and chloride ion. The equilibrium constant is Pb2 plus lead ion times chloride ion. It's not divided by the reactant, which is the lead chloride solid, because it's a solid. Okay, since it's a solid, so you have to pay attention to that S. It's not in the equilibrium expression. So we don't consider solids. So you look at the next one. Let's take out the solids. Okay, right away. You take out the solids, they're not included in the expression. And so our equilibrium expression, Kc, for the second reaction is just 1 over CO2, because that's the only one that's a gas. And the third one, I'm going to cross out the solids. And what we have is carbon disulfide as a product over sulfur, which in this case is a gas, squared. Okay, so those are the equilibrium expressions there. This writing equilibrium constant expressions is part of worksheet 10, so we'll get to that. In fact, maybe that's a clue to work on that now. So let's see, let me get out of this. Come on. Oh, the discard them. Okay. So we're going to go out. I'm going to switch the camera to my worksheet. Oh, come on. There it is. So worksheet 10, equilibrium constants and Q. So the you know, we didn't talk about Q. So I'm going to go back. I'm going to go back to my slideshow. Let me go back to my slideshow first, and then we'll come back to this. So I'll leave the camera on, so it'll be easy. It'll be easy switch. You can see it up in the corner while I'm doing this. Okay, so I'm going to just continue from where we left off. So let's go on. Next slide. This is important. Okay, so the units of Kc of the equilibrium constant depend on the specific equation, but we're not going to worry about units for K for the equilibrium constant. We're going to say it's a unitless value. In this particular example, hydrogen plus iodine is in equilibrium with 2Hi at 427 degrees C. Again, the temperature is included. The equilibrium constant is 54. So in this table, you can see that the concentration of hydrogen iodide and hydrogen iodide is different in each experiment. So in the first experiment, it turns out to be 0.1 molar for hydrogen, 0.2 molar for iodine, and 1.04 molar for hydrogen iodide. If you plug those into the equilibrium constant expression, you get 54. In the second experiment, the hydrogen concentration is 0.2. The iodide concentration stays the same, but the hydrogen iodide goes up. But the equilibrium constant expression is still the same, 54. I want to point out something. Well, we'll do this later. Maybe we'll come back to this slide later, in a later part of the chapter. In the third one, we've increased the hydrogen concentration even more. And what happens is the iodine concentration goes down and hydrogen iodide goes up. And when we plug those values into the equilibrium constant expression, we get 54. So this table shows that even though the concentrations can vary at equilibrium, the equilibrium constant stays constant. Okay, let's look at Q versus K. So remember, Q is our reaction quotient. That's product over reactants, and K is the reaction quotient at equilibrium. So let's look at that last example. So we showed that we can have lots of different concentrations, but when equilibrium is reached, the concentration values all, when plugged into the equilibrium expression, equal the equilibrium constant. What happens if the concentrations aren't the same? What happens if we have a reaction quotient, we plug in the values and we multiply them together, and they come out to be 54. Oh, so this is where Q is equal to 54. Well, what does that mean about the reaction, about this reaction? H2 plus I2 is in equilibrium with 2HI, 2 hydrogen iodide. Well, if Q is 54, that means the reaction is at equilibrium, and there's not going to be any change in the concentrations of these substances. So this is how we can use a reaction quotient to determine what kind of change is going to occur in the reaction, whether it's going to change more towards products or more towards reactants. Okay, that's what we're trying to figure out. Given a set of conditions and knowing the equilibrium constant, how is this reaction at equilibrium, or is it going to change? Does it have to change towards reactants or products to come to equilibrium? So here's another condition. So we have a set of conditions, concentrations, and we plug them into the reaction quotient equation, and we find out that it comes out to be 120. Well, 120, look up here, 120, Q is 120 now, it's much greater than K. So that means when it comes to this ratio, products or reactants, there's too many products, there's more products. So let's look at our reaction here. And I'll just use the same pen color. Look at our reaction. So here's our reaction. It means we've got too much product. So that means we have to lower the amount of product and increase the amount of reactant. So that means this reaction is going to have to go this way. So the product goes down and the reactants go up. So that's what has to happen. The reactants have to go up and the product has to go down. The way we describe this, we say this reaction has to shift to the left, or it has to shift toward reactants. And that's exactly what would happen. And how long would it shift? How is the product, is HI going to totally disappear? No, it's going to keep going down, and I2 and H2 are going to keep increasing until the reaction quotient turns out to be 54, the same as equilibrium constant, and then the concentrations will stop changing. If you remember the graph from the very first slide, we had N2O4 and NO2, and the concentrations kept changing until they remained constant. So that's what would happen in this case. Okay, what's next? A new reaction quotient, 25. Well, what's 25? 25 is much less than K. So that means we have way too much reactants. We have more reactants than would normally be observed at equilibrium. So let me erase this stuff here. So what's going to happen? We have too much reactants. So we're going to have to decrease the reactants. So these both reactants are going to have to go down. This means our reaction is going to have to go this way to produce more product. So this is going to have to go up. So if that goes up, that means our ratio will get a little higher and it'll keep going up. This shift will keep occurring until the Q is equal to 54, then it's K, and then it stops. The change will stop. The concentrations will be constant. So that's what's going to happen. The reactants will go down, the products will go up. We would call this a shift to the right. So this whole equilibrium is going to shift to the right and to form more products. And then it'll stop when the concentration of the products divided by the reactants is equal to 54. Then we've reached equilibrium. So now we're ready to do the worksheet. So let's go back to the worksheet. So let me stop the share this time. All right, and there's the worksheet. So you should be seeing the worksheet now. I'll make it a little bit bigger on my screen. I don't know if that makes a difference. So let's look at this worksheet. It's just calculating the equilibrium constant in Q. So there's just a general explanation at the top for how to write equilibrium constant expressions. And the first exercise is to write the equilibrium constant expression for the following reactions. So let's look at this first one. I'm going to zoom in. It's a little bit, zoom in a little bit. So it's calcium carbonate solid in equilibrium with calcium oxide solid plus CO2 gas. So our K, so first of all, remember what we're going to do is we're going to cross off the solids. They're not going to be included in the equilibrium expression. So K in this case is just going to equal the product, which is CO2. And that's all. So it's K is equal just to the concentration of CO2. So whatever that is going to be. All right. That's pretty easy. Let's look at the next one. So now we've got ammonia gas plus HCl gas in equilibrium with ammonium chloride solid. Oh, another solid. So let's get rid of this solid. And that means our equilibrium expression, we can put Kc here. I guess we'll put Kc in both those, is going to equal to the product. Well, there's no product in this expression over the reactant. So we're going to go like this. It'll be the concentration of the ammonia raised to the power of 2 times HCl raised to the power of 1. So there's our equilibrium constant expression for that second reaction. I guess the one thing I did check was to see if it's balanced. I was assuming these are balanced equations. So you always have to look for that, and they're both balanced. So I'm going to let you do this last one. So I'll put a circle around that one. You can do that one. And notice in this one, there's liquid water. So that L is important. Okay, next page. So this is a page where we're going to be manipulating equilibrium constant expressions. So it says determine the value of the equilibrium constant for the following reactions. Given that, here's our given. So this isn't part of it. We're going to make a little square around this. This is separate. That's our information. So we have 2NOBr in equilibrium with 2NO plus Br2. And then the second equilibrium is Br2 plus Cl2 is in equilibrium with 2BrCl. And equilibrium constant expressions and the values are shown on the right. So question 1, it says we have a reaction 2NO plus Br2 is in equilibrium with 2NOBr. Well, how does that relate to what we have above? Well, if you look at reaction 1, I'll call this A. I'll call this B. It looks like it's the reverse of A. So if you look at A, if we take 2NO, it's the reverse reaction going backwards. So the K for that, the Kc, is going to be equal to NOBr squared divided by, they're all gases, so that's true, divided by NO squared Br2. So if you look at that and compare it to K1, it's equal to 1 over, it's the inverse of K1. Determine the value of the equilibrium constant. So it's going to be equal to 1 over 0.014. So I can do that in my calculator. I plug in, whoa, there's my calculator. That's kind of cool. Okay, so I plug in 0.014 on my calculator. And then I have an inverse key. So I'm just going to hit that inverse key, which is right there. So I can do shift, see if that works. 71.4 it looks like, but it's 2 sig fig, so I'll just say 71. And these are unitless, so there's no units. So that's it. Let's look at the next one. I'm gonna let you do the next one. So the next one, put a circle around that, is 4NOBr in equilibrium with 4NO plus 2Br2. So what's the relation between question 2 and our A up there? This question 2. It looks like everything is multiplied by 2. So what do you do to the equilibrium constant? And the equilibrium constant that's important here is K1. So what do you do to K1 to match the equilibrium equation shown in number 2? Okay, I'll let you do that one. These are all things that we just covered in the PowerPoint. Okay, number 3 is NOBr in equilibrium with NO plus 1/2 Br2. Well, in this case, it looks like it's 2NOBr in equilibrium with 2NO plus Br2. It's A divided by 2. If we write the equilibrium expression for this one, we have Kc is equal to NO times Br2 to the 1/2 divided by NOBr. Let's look up here at this one. Let's look at K1. Well, if you look at the difference between K1 and Kc for problem 3, it's equal to K1 to the 1/2, or the square root of K1, right? If we take K1 and we take it to the 1/2, the NO2 becomes NO, the Br2 becomes the 1/2, NOBr becomes to the 1. That's what we've written for this equilibrium in number 3. So our answer in this case is going to be 0.014 to the 1/2, which is the square root. So here's my calculator, 0.014. And I'm going to do the square root, and square root key is, you can probably see it faster than I can. I don't know why I can't find the square root key. There it is, up here, square root. So it becomes 0.118 or 0.12, 0.12. Okay, so that's the answer. So number 4, the number 4 is an interesting one. So number 4, let's say I didn't want to move that, I'm just going to move this. Okay, number 4, 2NOBr plus Cl2 is in equilibrium with 2NO plus 2BrCl2, or 2BrCl. Let's look at our equations. Well, it looks like what's going on here, we have NOBr plus Cl2. So let's look, NOBr plus Cl2. It looks like maybe if we added those together, we'd end up with this. And indeed, that's what we're going to do. If we add these two equations together, we'll end up with this one. And that's all we have. This is related to Hess's law, which you did in Chem 2A. So if we add these two together, what do we do with the equilibrium constants? We multiply them together. So what I'm going to do is I'm just going to do that up here. I'll let you do it. I'll just do it. I'll just talk through it. You guys can do it on paper. If we take NO squared times Br2 divided by NOBr squared, We multiply it times BrCl squared over Br2Cl. You can see that the Brs are going to cancel. And what we're going to be left with is NO squared over BrCl squared divided by NOBr squared Cl. So our products are going to be NO and BrCl, and the reactants are going to be NOBr and Cl2. Does that match our equation in number 4? It does. Products are BrCl, NO, so that's going to be on the numerator, and the reactants are going to be Cl2 and NOBr squared. That's in the denominator of our equilibrium expression. So that works out. So I'm going to let you guys do that one. And then I'll work this last one. So for this reaction, hydrogen plus iodine produces hydrogen iodide. The equilibrium constant is 54.3 at 700 degrees C, or K, sorry. The non-equilibrium concentrations are H2, I2, and HI. So determine Q. So let's write Q. So Q is going to equal to HI squared divided by H2. These are all gases. And we're going to plug in these values. So we're going to plug in the value for H2, HI, and I2. So HI is 0.0424. And H2 is 0.00623. And I2 is 0.00414. So if I multiply all those together, or just complete the calculation here, 0.0424 divided by 0.00623. And then because the 004, I don't multiply these together, I divide again. This is 0.424 divided by 0.00623 divided by 0.00414. So I'm going to divide by 0.00414. And that becomes 1,644. And that's probably a few too many sig figs, but this is greater than K. So, and this is K at equilibrium. So sometimes we put an EQ here instead of a C to indicate that it's the equilibrium constant, but that's what K is. That's kind of redundant because K means it's at equilibrium. So the 1644 is greater than K. So that means we have too many, what, reactants or products? I think it means that the product, the I2 is too big. So that means our reaction is going to have to shift to the left. We're going to have to decrease HI, not I2, the HI. We have to, HI is too big. We're going to have to decrease HI and increase hydrogen and iodine. So this reaction is going to shift to the left to increase the reactants, which will make the reactant concentrations a little higher. That'll make this number lower. And it'll keep decreasing until Q is equal to K. And then the reaction, or the change in concentration will stop. The concentrations won't change anymore, and they'll be at equilibrium. So determine and decide which way the reaction must go to achieve equilibrium. It must go to the left. So I'll just write it down. Must go to the left. So I hope that makes sense to you. And that's the end of this worksheet. So let's go on. I'm going to shift back to a screen share, and we're going to continue on with this PowerPoint. So this time I'm going to just share the PowerPoint directly. So you should be seeing the PowerPoint now. And maybe the worksheet up in the corner. So let's continue. The next part of this PowerPoint has to do with gas phase equilibria. Let's see, you already did this. So I'm going to skip through this pretty fast. So gas phase equilibria. So here we have an equilibrium, a generic equilibrium of gas phase reactants and products. And the Q and the K may be expressed in terms of partial pressures. So that's what's shown at the bottom. And we'll use the subscript P to indicate that there's pressures. And in order for this to happen, the reactants and the products that are in the expression must all be gases. Now, if you have a solid in there or a liquid, that's okay because they don't appear in the expression. But if there's an aqueous in there, then you can't use pressures. Okay, so if the chemicals or the compounds that are in the expression, the reaction quotient expression or the equilibrium constant expression are all gases, then you can use pressures to describe equilibrium. So let's what I want to do here is to compare the equilibrium constant in pressures with the equilibrium constant in concentrations, in molar concentrations. So if our QP is equal to KP, this is what was on the previous slide, is the pressure of B to the exponent, or to the coefficient, divided by the pressure of A to that coefficient. We can use the ideal gas law to see how that relates to molarity. So if we take our ideal gas law and we rearrange it for pressure, we see that we have nRT over V. Well, this expression, the N over V, this part of the rearranged ideal gas law, is molarity. That's the concentration of A or B in moles per liter. So V has to be in liters, N is in moles. That becomes molarity. So substituting MRT for P, we get the QP equals KP, and we have the molarity of B. Or we could write, instead of molarity B, you could write what we usually write would be B in brackets. That's what the B in brackets means. It means the molarity of B over the molarity of A raised to the power. So this is, let's see, A is to the X and B is to the Y. Let's see if I can write that. That my X didn't come up pretty good. X. That's supposed to be an X down there, A to the X. And then we can take out, so over here we have A to the X over B, so excuse me, B to the Y over A to the X times RT to the Y over RT to the X. Well, we can combine this. We can say, well, this part is the same as our KC. So we have KC times RT to the Y minus X. Well, the Y minus X becomes the delta N. So let's look at that. Let's see. So a generic way to write that is like this, and I'm going to erase those. Let me erase some of these things here so it's a little clearer. Okay, so we got that. And We have a general expression. This is an important one. I would write this one down because this is one you can use if you have a problem like this. You need to write that down, okay? And maybe write this down too, that the delta n is the sum of the y minus the sum of x. So that's how we relate the gas equilibrium, the gas equilibrium constant to the concentration equilibrium constant. So we have another worksheet to do. I'm going to flip over to that one. I think that's it. Let's see if there's anything else. No, that's it. That's the end of the slideshow. So let's go back to our worksheet. So we have another worksheet here. Worksheet 11. Worksheet 11. There's a lot of work. That's worksheet 11. Okay. It says write the equations for the conversion of Kc to Kp. So Kc to Kp. So we want to write down the expression. Well, if you wrote down that expression that I told you before, it's this: Kp equals Kc times RT to the delta n. And so if we look at this particular equilibrium, let's look at our coefficients. Coefficient of 1, coefficient of 1, coefficient of 1. So our delta n is going to be, so this expression is going to be Kc. So to calculate Kp, if we know Kc, times RT, delta n is 1 plus 1 minus 1, 1 plus 1 minus 1, and that's going to equal 1. So our Kp is going to equal Kc times RT. Well, R in this case is a gas law constant. It's the in liter atmospheres per mole degree K. So T has to be in K. So let's pay attention to that. So T must be in K. And R is our gas constant, which is 8.124, something like that. You'll have to look that up. So this is our gas constant. So you need to have that handy too. And it's in liter atmospheres per mole K. All right. So the next problem, it's the same thing, write the equations for the conversion of Kc to Kp. I'm going to let you do those. Okay, those aren't too hard. It's the same generic, it's this equation, and all you have to do is figure out what the delta n is. Let's go to the last one. If Kc is equal to 0.28 for the following reaction 900 C, what is the value for Kp at this temperature? Well, let's figure this one out. So Kp is equal to Kc times RT to the delta n. That's going to equal, Kc is 0.28, 0.28 times RT, and R is, okay, I'm going to find out what R is. Give me a chance here. So R is kind of had it wrong. R is 0.0821 liter atmospheres per mole K. So we have 0.28 times R, which is 0.0821 liter atmospheres per mole K. Times temperature. Let me put this in brackets. The temperature is going to be 900 plus 273 to get it into K. And that's going to be to the power of delta N, which is the coefficients of the products minus the coefficients of the reactants. And so we have 3, 2 plus 1 is 3. 3 minus 4 plus 1 is 5, which turns out to be -2. So that's it. I think I'll stop there. I don't need to do any more, but that's how you would solve that one. I think the only difficulty, there's one little trick here, and that's just to remember to convert the temperature into Kelvin, because temperature is usually given in Celsius. So I think that's it. That's it. So I'm going to stop now and just end this lecture. This this worksheet, number 11, is one that I want you to turn in. So when you complete it, you can go ahead and turn it in. The other worksheets will be for the later section of this chapter. The other worksheet I want you to turn in will be the later, one of the later ones in this chapter. So take care and happy studying. Goodbye.